Near the end of the previous video, I had this calculation up, and I actually remember now what it was. I had gone online and I had found a heat of solution value for sorbitol, and it was bigger than the one I had found from the other source. It was about 26.5 calories per gram. So what I had done here, as you can see, is I had used the fact that there are 182 grams in a mole. The fact that the conversion between joules and calories is 4.18 joules for every calorie, and at 1 kilojoule has 1,000 joules, and had done all this math and unit canceling, and moles survived and kilojoules survived, so I had 20.2 kilojoules a mole positive value for that. And that's actually much closer to what we got in some of our lab results. In fact, I think one of the groups got 18 or 19, one of the classes. So that's what that was. What I'd like to do, though, primarily here in this video is look at solubility again and try to explain it using enthalpy and entropy to explain like why some things are soluble or not. So the predictions that can be made using enthalpy and entropy are what make it extremely valuable. So just a quick review here. In the dissolving process, there are particles that need to be separated from each other. Ionic things tend to break apart and give separate ions. Molecules may go apart from each other, like a glucose and a glucose may no longer be associated in a crystal, but they themselves don't break apart into pieces. Molecules are covalently bonded and tend to, especially if they're nonpolar, tend to not break apart. They may go away from each other, but the molecule itself stays in a C6H12O6 kind of form. There are situations where molecules will partially dissociate, like certain weak acids will give you a few H pluses off the molecule only from certain H's. But regardless of whether you are dissociating ions or just moving molecules apart from each other, or even having some molecules form a few ions, it's going to take energy. And then when the water molecules surround the ions or the molecules, if it's a covalent thing, this process called hydration occurs, and it kind of stabilizes the particles in solution. And during this process, energy is quite often released, a good bit of it. And then depending on the balance in these processes, there are a couple of inputs there, separating and expanding the solvent to allow the material to be hydrated. And then you have this process of, the hydration process is the one that stabilizes them, gives off energy. Then you can get a net flow of heat in or out, and we usually call this the heat of solution, or the delta H of solution. Usually it's something like kilojoules per mole. If you see in the book the top of 473, you can see some values for this and some information on it. So we've seen all that before, but let's try to do a little predicting here. It can be tough, but you can kind of see how this works. Let's look at our lab as an example, because it is kind of a good one. Let's say a material has a positive heat of solution, meaning energy has to go into it, which is what would cool your mouth with the sorbitol or the other polyols. And this, of course, can happen. We've seen it. One might think this would keep it from being very soluble, since that's energy flowing into the thing. That kind of goes against what we said is the trend of the universe. But as it dissolves, the entropy is going to get more. There's going to be greater disorder. It doesn't matter if it's ions or molecules. If they enter into the solvent and become dispersed and randomly move around, we got a greater freedom of movement there than we did in the crystal form. So the entropy becomes greater. This is the key. And let's say that at room temperature, T multiplied by the delta S is a pretty big number due to this change of entropy, delta S, that's happening, which is a positive because it's an increase of disorder. So it's possible at room temperature, under the conditions that we're describing, that if that entropy change is a big enough deal, it could drive the process. It could overcome the fact that energy does not want to spontaneously flow into that in the form of an enthalpy change as a positive enthalpy. And if you could get the entropy term to even be more dominant, like for example, raise the temperature, so heat it a little, and this is going to go into that equation. You remember, I don't have it on this screen, I'll write it, that delta H is equal to T delta S during a thing at equilibrium, like for example, say crystals sitting there going through the dissolving process in equilibrium with the solution. So if you raise that temperature, you help this term even more. And as you know, that describes the solubility of a great many substances. When you warm up the solution a little bit and give it a little bit higher temperature, generally it dissolves better. And the whole reason it does is that even though putting in, and by the way, if you are putting energy in to warm the solution, that doesn't hurt either, because you might actually be contributing some of what's needed here in the enthalpy input if you do it enough. Let's take a look at another example real quick. Let's take boiling. When you boil things, I think it should be pretty clear to you that the entropy is going to increase. But the downside, once again, is that you usually have to put energy in from the outside to do this. You know, they're fighting again. It doesn't want to allow that energy to just spontaneously go in there. So how does boiling even happen? Well, it's the same deal. Once the temperature becomes high enough, then that T delta S, the T delta S term, sorry for the interruption, which has a favorable entropy change because we're getting into the gas state, it's very random, that balances off any enthalpy input you have to make, and in fact it reaches a state of equilibrium where the energy input of delta H is being converted to entropy. And that's going to happen, that balance is going to be met at a certain temperature, and this is why boiling occurs generally at a certain temperature. Of course, we realize that the outside pressure can lower some of the requirements and actually change that boiling point, but it does still have to equal a balance where the delta H is equal to T times delta S. So in order to make this just a little simpler to keep track of, maybe, a fellow by the name of Gibbs defined a quantity to help us keep track of this. Whether or not something can actually occur at a certain temperature. Can it be going on? Can it be going forward spontaneously? And we call this number that he learned to calculate, which is actually just based really on the balance between these. We call it the Gibbs free energy change for the system if we're doing a delta. For any spontaneous process, the free energy of the system's got to drop. That's got to be in a situation between delta H and T delta S where that's true. The delta G change then has to be negative. And if it is, that tells us the thing can be spontaneous, it can happen. It gives us a way of predicting things that are likely to naturally occur. The equation for this is actually delta G is equal to delta H minus T times delta S. To my opinion, this might be the mother of all thermodynamics equations. Now, for anything that's like that boiling situation we described earlier, like where energy of enthalpy change is coming in, heat flow in, is balanced by entropy as it goes to the gas, and so at a certain temperature it'll sit there and boil. If you're in that situation, then you're at a place where delta H and T delta S are about equal, and delta G becomes 0 when you subtract them. That would be for any system at equilibrium. It would be in a condition of that. But if you're actually going to have an actual change of the system that involves a change in the free energy, the delta G has got to be negative. And if it is, it can occur. If you calculate using these numbers of delta H and T and delta S, and you get a delta G that is positive, then it's not going to happen spontaneously under those conditions. That's not to say we couldn't up the temperature or do something to help it, but it's just not going to occur under the conditions we've calculated. Kind of also keep in mind that a positive delta H and a negative delta S are against the second law and are not really favored to occur. And the opposite is also true. If you can lose energy and get more disordered, that's pretty likely to occur. And we could summarize the kind of things that will happen and what won't just by looking at those numbers. Let's see if we can kind of take a look at what would happen if the delta H was positive. Well, that's an inflow of energy. So this kind of unfavorable from the laws. On the other hand, a positive T delta S, where the entropy is going up, that is a good thing as far as, the universe likes that to occur. So we have to then say, would it be spontaneous or not? Well, since this is equal to the difference here, if delta H is positive and we want it to come up negative, we want this to come up a negative number, then it's going to depend on how big the T delta S term is. In order for this subtraction to come up negative, T delta S needs to be bigger. So the answer to is this spontaneous or not, the answer is maybe. This is going to be negative if T delta S is large enough. So basically this will be spontaneous more likely at very high temperatures. So this would be a process like maybe the boiling of water. You got to put energy in to make it happen.
There was some money.
All right, I'm back. So anyway, this could be like the boiling of water. You got to put energy in, but you're getting a positive entropy change. So the entropy is kind of the helpful factor if you want this to take place. And the temperature needs to be at the right temperature, and fairly high temperature there to boil water. So let's take a look at the next one. You got a positive delta H. Okay, not so happy. And you have a bad entropy change. Well, if you look at the math here, any positive number minus a negative number has got to give you a positive. It's got to. That means, is this spontaneous? The answer is, this is never going to happen on its own. There is nothing in the universe that is spontaneously going to take in energy and get a negative delta S, which is more organized. There's no way. Never going to happen spontaneously. That would be like the forest redoing itself after the fire. Now the next one is sort of the flip side, I think, of that. If you look, a negative delta H would be energy coming out. So as far as the second law is concerned, yes, great. Also a positive delta S. These are both what we call favorable changes. Like it wants, the second law wants to allow this kind of stuff to happen. So this is always going to give you a negative minus a big positive, which is always going to give you a negative number. So will this happen spontaneously? The answer is always. If you have a process that's giving off energy and getting more disorder, you ought to expect that one to happen. And then finally, we got a case down here where they're both negative. Well, this is favorable because systems like to give off energy, but this implies more organized and not too happy. So this is maybe, who knows, on the sign of this. So is this spontaneously? This is a maybe. But in order for this one to work, we need the T delta S term to be kind of little. So this one is much more likely at low T. That way, that frowny face on that entropy term cannot dominate because T is little and it makes the T delta S term not get so big. So kind of a little summary, delta H and delta S can fight each other like both, and if that's the case, that's probably never going on its own. They can both be in favor of something occurring, and that one's probably going to happen pretty readily. And then if they are opposing, like one of them's favorable, but one of them's like, no, it's getting more organized, kind of, so it's against, then it depends on T. That balance is what controls whether things happen or not. So we will catch you later.